Yeah, thank you, dear Chairman, for the nice introduction and for setting up this conference and for inviting me to give a speech here. Hello to all from Australia, where we have evening time now. I'd like to talk to you about two molecules which make eminent fuels, ammonia, which is considered as a hydrogen carrier, and biodiesel. I will talk largely about ammonia in using it as a fertilizer, but because that is our research essentially, but the conclusions can be transferred to energy, and the biodiesel application is purely on energy. I like to say that my work comes both from the University of Adelaide in Australia, where I majorly work, and from the University of Warwick in England, where I have a major European grant on the ammonia manufacture. And I'd like to highlight my two co-workers, Nam Tran from Australia and Jose Osorio Tejada from the University of Warwick. Now, we work very applied. You can make fundamental research or applied research. In this case here, at least what I present is mostly applied research. So I like to give my credits to, so that you see with which companies we work together. Jürgen Lang from Evonik, who introduced me to the non-thermal plasma. Chris Mesrobian from Monolith company, who will be and is a major player in making hydrogen by thermal plasma. We work with farmers as we go for fertilizer, and here's Craig Butler, who is simple words the head of the South Australian Farmer Association, and that is around 400 to 500 farmers. We work with him on green hydrogen for grain growers. Lawrence Curtin in Western Australia, who converts whole mines into farming land, and green energy plays a major role in the conversion of mines. Peter Wadewitz from Peat Salts, who got the Order of Australia, which is the highest medal which you can get in Australia. That comes from the Queen, so he's a very highly decorated person, and he works on biomethane gasification. And I already mentioned some of those names, and I have to mention Laurent Fulcheri, who made what only few researchers ever made. He brought with Monolith company his thermal plasma to a commercial scale. And his contribution is considered so important by Monolith that they created a Laurent Fulcheri Prize, an award of his name. I have a major European project which keeps me busy in Warwick, as I said, and that is the ESG synergy grant scope. And just to give an idea, this is about 10 million euros, which is about 13 million US dollars maybe. Now, supply chains are very important, you know. This thing here is 1 week old or 2 weeks old, and I'm cited 3 times in The Guardian, and I think I'm the only researcher from Australia cited there, what we can do to face the urea supply chain in view of the diesel additive at fuel, which really is a major risk for Australia. We can come to a situation that all trucks stand still. In UK, fertilizer companies were closed virtually overnight. A company who makes food packaging, which is associated to that, were closed overnight. And the Tesco supermarkets did not contain for a while frozen food. So you see, supply chain issues, that is not just something on the horizon, that is real. And it has to do here with ammonia, because I didn't mention urea is naturally made from ammonia. That is the relationship. Now, we saw this actually long ago. We saw this in 2017 with Evonik, and we said all those global supply chains at one point will have their disadvantages. So let's make the fertilizer at best where it's needed, and that is at the farmer. So the farmer has his own factory. Naturally, this is a bit naive picture, and it looks a bit still like on a playing level. But here you see 2021, we have a project together with the head of the Farmer Association, one chief person who sells credits in the hydrogen cluster in South Australia. And you have to know that South Australia already has now a very large share of renewables and hydrogen. So probably we will become world leading in the use of hydrogen. We will soon have up to 30% of the energy from such sources, and it increases. So there's a big chance for ammonia consequently. Now, the business case developed here, and that is made with all the gentlemen which I've mentioned at the beginning, is to go from food waste, so from manure, to methane by biogasification that you see on the left side here. Then you have the methane, and the methane is split by thermal plasma into hydrogen, which actually is only the co-product. The more valuable product even is activated carbon. You can do a lot with that, but I don't go into details here. I focus on the hydrogen and how this is converted by low temperature plasma. In the second step, the yellow plant, to ammonia that goes to the food to fertilize the crops. The crops are eaten by the animals and we come back to manure. So this is a kind of circular process. We have published this. And in this presentation, I just focus on the making of hydrogen and ammonia. Yeah, we oppose making it by renewables or by fossil fuels, and I think you're very much aware of that, so I don't go deeper here. Now, the whole point is to make the fertilizer not globally anymore, at least not only globally. Australia is a big country, it's actually a continent, so it's perfect for such considerations. We can talk about regional supply at a state level. This is South Australia, more or less what you see here. This is the larger Adelaide area, which I call local. So there's a difference between local and regional. And then we have a farmer collaborative who might consume 15,000 tons per year fertilizer still, which is a lot. And they are rich enough to build their own plant, for example, in the McLaren Vale, which is one of the 3 major wine regions around Adelaide. So remember with these 3 scales, regional, local, and at farm. Now, you see here the current situation is several plants for ammonia in Australia, or a few, not several. But the most important sits in Pilbara, that is at the northern western edge of Australia. And that's the region where all the big mines are and also where a lot of farming is. So there they make hydrogen and there they make ammonia, and Yara company operates that. And from there it's transported over thousands of kilometers to the farming regions, which you see here. And naturally, a lot of the fertilizer is important. You just saw the message. Now, the right picture shows an opposite situation. Everything is made locally. So S is the hydrogen manufacturer, I should explain, and P is production, is the ammonia manufacturer. So we distribute all these plants in the farming regions. And the farming regions consume a lot of N fertilizer, up to 350,000 tons per farming region. You see here, all in all, 1.6 million tons N fertilizer, and in total, Australia might consume 2 million tons, just to give you an idea. Now, what we consider is a classical case, and again, I think everybody in this conference will be aware what the Haber-Bosch process constitutes, and that hydrogen is made by steam methane reforming, and then we have the Haber-Bosch reaction to give ammonia. Now, there are different scenarios. We can use electrolysis, and suddenly we take hydrogen out of water, or in the thermal plasma process, denoted here as TPMP, we take hydrogen out of the methane, and then we go in a mini Haber-Bosch or in a plasma reactor. So that's a different scenario and use renewable energies. And on a farm scale, we even talk in a way seriously about the chemical farm on the truck to make ammonia or nitric acid. And ammonia, and Evonik has called that chemistry on wheels. Now that this is not all dream, I show here, and I mentioned and highlighted Monolith company, who are chased by all big global companies now, by Mitsubishi, by SK collaborations. They have billion contracts. That is the 3rd largest Korean company after Samsung. And recently they made a big contract with Bridgestone as a car manufacturer because they make carbon black. They make carbon, what is called turquoise hydrogen. Decima would also use that term in Germany. And that is a kind of hydrogen which still has some CO2 footprint, but not a major one, which maybe can be even repaired, but it is as it is. It is not a green hydrogen, it's a turquoise hydrogen. But it's a very good point about it is 6 times more energy efficient than electrolyzers currently, and it is at scale. It can make up to 250,000 tons of urea. The plant which I've just shown here, yeah, that can make 250,000 tons. And the electrolyzers, to my best knowledge, are not at that scale. It's a good technology to consider. We make fundamental science. I just want to mention it and not to explain it. This is how you classically would make low temperature plasma to make ammonia or nitrates. We made it in the European project MAPSIN, where I developed the technology together with Evonik. But that is all not energy efficient. So we go for new concepts in the new EU project scope. And we make microplasma with microstructure chips, as you see here, micro dimensions. And we hope this is more efficient. I don't want to go deeper into detail for reasons of time. Now, the plant on wheels that is existing, European Union for almost 10 years in the Horizon 2020 program and in the former FP7 program, founded what they call future factories, not only in chemistry, but in all manufacturing industries. And in chemistry, the development of all big companies, and virtually all were involved, Bayer, BASF, and so on, and Evonik, they made modular containers, which are even transportable, as you see the container here. And that is made in a project, I'm not sure if you can read it here, copyright, which I headed. So I was a coordinator of this project, an initiator, and that was about 25 million euro funding, so more than 30 million US dollars, so quite big projects where we built 2 such containers. Now, I always say you cannot change the world from the desktop. You have to go where it actually happens, the manufacturing. And in the case of fertilizers, we go here. This is Peter Wadewitz, which I highlighted before, who got the highest Australian medal. We go to farming regions. This is Clare Valley, if you're a bit familiar with Australian vines. You see the farmer, that's the orange guy here, Laurent Fulcheri, who brought the thermal plasma to scale. And that is Craig Butler, the head of the farmer organization. And yeah, you have to know something about soils. It's not enough to bring the ammonia in any kind into the soil. The ammonia has to be consumed by the plant. And this very nice drawing is from Craig Butler, and it combines on the left side all the options with renewable fertilizers now, which are also renewable fuel options. And the soil science, which you need to have. You need to ensure that the ammonia is taken up by the plant, and you have to know a lot about microorganisms, about encapsulation. So there's a lot more to do. Now I come to some results from my postdoc in Warwick. This is a life cycle analysis. It shows all kinds of impacts on the left side. If you see global warming, human carcinogenic toxicity, so it's on the rivers, it's on the humankind, it is on the air, on the atmosphere. That is a typical life cycle analysis if you have ever seen it. Everything is then given here with color coding, and the color coding shows the origin of the environmental impact. And if you know the origin, you can do something against. That's the whole idea of such life cycle assessment. And I always say, if you never have seen it, look at the most dominant colors. One is green. This is the raw materials, and that is trivial in a way, or that is known. Every synthesis is determined by the raw materials. If you change the raw materials, you get a greener process. That is common way of doing that. But that's not what we want to do here, or not majorly. We have to look on the blue color, and that is road transport. I told Australia has thousands of kilometers, and Haber-Bosch consumes a lot of energy. But as you will see, almost 1/3 of that comes from transport alone. So you can save a lot of CO2 if you eliminate transport. An initial guess was that it's 25%, but you will see later a more finer calculation. I will explain what finer means. So keep the 25% in mind. Now, if you look on the different life cycle impact categories, and again, on the left side, it starts with global warming, it goes down to the toxicity, and you look on all those scales, farm scale, regional scale, local scale, you see they're very bad with grid energy, so with fossil energy, and that is not surprising because that is not a green energy, and generally they are not as good as a world scale Haber-Bosch process. But if we combine it with renewable energies, then we compensate the disadvantage in production against Haber-Bosch. And we have a major advantage. So there's really a major reduction if we use renewable electricity. So we can say those technologies in principle have potential. This is only environmental here. This is not about costs. I come to cost in a second. Now we made, I have to speed a bit up, we made a very detailed transportation analysis. As I've said, we looked for all these thousands of kilometers in Australia for each road track, for each gradient as it is. We looked for the Australian trucks and not Euro trucks. So we looked very much in detail. Long story short is it amounts to 30%, so even more, and you can save a lot of tons CO2 just by the transportation, and similar things can be found for eutrophication, for ozone formation. So local transport pays off. Now, if we look on the, what is given here is tons per CO2 equivalent per ton of ammonia. So you see you produce a lot in the Haber-Bosch case. On the left side, the two bars, that is a classical case, but you also get something back in this case by steam credits. Now, if you look at the combination of high temperature plasma and mini Haber-Bosch, this is much less in CO2 as I've shown before, and is compensated in this case by carbon black credits. The electrolysis shows the same picture and has oxygen credits, which are actually higher than the carbon black credits. And finally, we have the combination of electrolysis and low temperature plasma. This is worse because the low temperature plasma is not as good as the electrolysis or the mini Haber-Bosch plant. Now, finally, we have made cost analysis, and this is given here for all the four combinations given before. And we have investigated hundreds of cases. That's why you see so many cases here. And I don't detail now what these cases mean that is given in the paper. The main point to make here is that the thermal plasma plant and mini Haber-Bosch on a local scale can be almost as good as a global scale steam reforming and Haber-Bosch, and the water electrolysis is not 1,000 miles away for it. Now look in the middle, we have the production plant in Alice Springs. This makes the hydrogen, and it still delivers it through the farming regions where the ammonia is made. Now, if you make the hydrogen and the ammonia together in the farming region, so no plant anymore in the middle at Alice Springs, the situation becomes even better. If I would go back and you would compare bar by bar the cost values, which is US dollar per ton ammonia, you would see it has gone down, and the ammonia on the world market costs round about between $300 and $400. It always fluctuates a bit. So we are in the right range. Also, this is cost here. And what I talked, it's a price, so it's not the same. So there's still some job to do. I skipped that slide for a reason of time. And I finished the ammonia story and come back to the smaller biodiesel story with something we presented at the Royal Adelaide Show. That is a fantastic event for public promotion of research results. And we made two 3-meter long and 1 meter wide models about the old economy, who looks a bit gray with its big factories, and the new economy at farm plant, which is greener and has the trucks with the fertilizers. And 8 architecture students were 3 months busy with that and put a lot of effort into it. And that's a nice way to make the public aware about our results. Let me come to the biodiesel. Here we go for the resource way to make the environmental profile better. That is, as I said, a common way, and we don't use resources which are made from fossil resources with fossil energy, but we use a waste resource, which is grease trap rate. And I will show you why we use that. If you have not seen it, I think you all know this. This is a reaction to consider, which makes the biodiesel. So this is deesterification reaction. And the whole circular cycle here is, it comes from hospitality, which produces a grease trap. And there's a biodiesel plant, which makes a biodiesel, which is transported to the hospital. So that is the circular way to consider Now, why we use grease trap waste? Simply because there's so much more than all other sources, at least in Australia. You see here comparison to used cooking oil. So there's a lot of grease trap waste around. And if you look, that's not only in Australia, that is given in China, US, and other. And this is only part of the table. The table is longer in the paper. I just cut it off because otherwise you cannot read. As usual, there's a big disadvantage in the grease trap waste. It has a lot of impurities, nasty impurities, such sulfur contents, phosphorus contents. This is higher than for other biodiesel resources, and that has to be reduced. And the conversion is usually not high. That is what is denoted by FFA. So you have to have a high conversion of fatty acids. So this is to be solved. And here you see the whole process. So first of all, you have to extract the grease trap waste. That is what is meant by FOG. So O stands for oil and G for grease. And there's an extraction process. And I will not talk all about this. So you cannot just pump the waste into the chemical reactor. Yeah, there's some process before it. Then you have the chemical reactor with a catalyst, and you see there's a quite complex purification process probably required with a lot of recycling of materials. And we also think, but I don't detail this, just to mention that nanoparticles could play a major role here in the purification process. So there's a lot of work done on the purification, but this is what I will not show. We will do that in future. I will show our work on the chemical reaction. Now, it's an enzymatic process, as I denoted before. And we used enzymes on a laboratory scale, but we also used commercial enzymes like Novozyme or two other enzymes, which are specialized enzymes from a small Swedish enzyme company. And you see, we come to quite high conversions relatively, and with the flow technique, it's even higher, up to 80%. Now, we use continuous flow. That's what I do. I do plasma as disruptive technology, and I do continuous flow as disruptive technology. We used a relatively simple flow reactor, which is a packed bed reactor, and you have two pumps to feed the reactor. Now we made a design of experiment study to get an idea how the parameters depend on each other and what is finally the best process configuration. In such studies, you typically compare your experimental results with simulated results, and you see that fits quite well for the batch. And also the flow technique is not too much different, a little bit more deviations for the flow technique. And then we made the typical plots where 3 parameters are plotted against each other. You see here the given the conversion, the catalyst loading, and the reaction temperature. 3 more, actually 6 are given in the paper. I cut 2 off to make that visible. I don't want to discuss them in details. It's given in the paper. You can draw conclusions from that. And although there are differences to the same parametric dependencies in batch. Now, with that in mind and seeing that everybody here in Australia and the whole world talks about artificial intelligence, about learning, and that such methods like this BioE, which is done in Excel sheets, is maybe old-fashioned. So what can flow process automation, which is very strong in my field, can do? And you see, we listed up some advantages in the continuous process. It's most notably you consume less materials for the whole process, yeah, all around if it's a catalyst. But you also can make faster test throughput frequency. You can make more tests per time. So a lot of experts believe that continuous is a better technology for the process automation. And we also gave that kind of plot here, which we consider how you stepwise can make the process automated from process monitoring to self-optimization, dependent on the job which you like to do. Finally, and I'm on my last 2 slides, we made a cost study that is now another paper on 2 biodiesel processes. I don't go into detail here, and it's not so obvious what is the difference with all those components. In one case, we added a solvent to support the purification of this grease trap waste. Yeah, you remember that the purification is a key. Now, the solvent makes the process more costly, Question is, does it pay off by better purification? Now the answer is given here, route 1, which is without the solvent, and route 2 is with the solvent. And you see the route 2 is more expensive and route 1 is close to the average diesel price. So the answer was negative in this way. No, the solvent does not pay off, at least not as it is given. So we really need some good purification processes. It cannot be done internally in the reactor. And we also made some detailing of the CAPEX and OPEX costs here. I'm at the end of the talk. I'm not sure if the organizer will go for questions, but if so, I think we have 3 minutes for that. Thank you for listening.